Hi, everyone. Good afternoon. I am Mohammed Saad Al-Din. I work at the Insight Center in UCD, University College Dublin in Ireland. Today, I'll be presenting our paper titled An Orthogonal Classification Layer with Kasami Sequences for Discriminative Feature Learning in Neural Networks. This work has been done by me and my advisor, Brian McNamee. This work mainly focuses on the output or the classification layer of the neural network. So for classification problems specifically, where a data class, a data point need to be classified to belong to one of a set of classes, we can view the classification network as two stages, where we have the network layers consisting of all the hidden layers, all the way from the first layer to the last hidden layer. And then we have the classification or output layer, which is supposed to give us our final output or our final probability that tell us the likelihood of this specific input X to belong to which of the data classes. So looking at these two stages of the classification neural network, the network layers all the way to the last hidden layer basically applies a series of operation or transformations to the input data X in such a way that it translated or projected into the latent domain, or it converted into a latent representation. And the objective here is mainly grouping all data points belonging to the same data class to a unique and similar latent representation, so that if all the data class or the data points belonging to the same class will be projected or transformed to a latent representation, to a unique latent representation that group them together, that is kind of represent this class. Then after the network layers generated this latent representation of each data input X at its last hidden layer, usually referred to as H. So we have now H, which is equivalent to f of X, where f is the function representing all the network layers and all the operations and transformations performed by the network layers. Then this latent representation is then fed to the classification layer that give us our final output Y, that indicates the probability of the data class X to belong to which of the available data classes. Usually, conventionally, the classification layer consists of a set of output neurons, where each neuron is associated with one of the input data classes. So if we have n data classes in our data set, then our output layer or our classification layer will consist of n individual neurons. And all these neurons together are formed in a fully connected layer, where the input, the latent representation coming generated by the network layers is fed to this fully connected layer, where it basically get dot product with the individual weight vectors W0, W1, Wi, all the way to Wn minus 1 of each neuron associated with each data class. The final output Y0, which is basically the dot product of the latent representation H with the weight vector of that specific output neuron 0, will tell us the probability of the input data X to belong to data class 0, same wise for data class 1, all the way to Yn. So basically, this is how the output layer or the classification layer conventionally performs or work in classification neural networks. Here in this work, we propose an addition or a new classification layer where we fix the weights of this classification layer to an orthogonal set of codes, specifically in this work for Kasami codes. And we are going to see how this will allow the network to train in a better way and provide higher accuracy results. But first, let's talk about the Kasami codes themselves. So Kasami codes are basically orthogonal, a set of orthogonal codes commonly used in wireless communication and signal processing when mixing signals or multiplexing, or for code division multiplexing mainly. And each set of code, each code consists of is a binary code consisting of where each value is either 1 or -1. And the main property of these orthogonal codes, and Kasami's in this specific example, is that they have very good correlation properties, meaning that when the dot product of any of these codes with itself give a very high value, while the dot product of that any code with any other code among that set of codes provide a very low value. So these codes are mathematically designed to be orthogonal to each other so that they only provide high output value when they dot product with themselves, what is called autocorrelation, while they provide very low value when they dot product with any other code within that set, which is called, which is basically the cross correlation value of them is very low. So Kasami codes are not the only orthogonal codes available. There is a number of other orthogonal codes used, very commonly used in communication and signal processing, as I said, such as Barker, Walsh, Zadov-Shaw, Hadamard's M sequences, and Gold sequences. Some of them are binary, same like Kasami. Others are continuous codes, and even some are complex, like Zadov-Shaw code, for example. We decided to work with Kasami code in this work, but we are intending to examine and evaluate other codes as well in the future. Back to our classification layer and our classification network. Basically, we fixed the weight of the classification layer to a set of Kasami codes by assigning one Kasami code to each neuron as its fixed weight. For example, we have a set of n Kasami codes. These n Kasami codes are assigned as fixed weight to all the n neurons in our classification layer, where for neuron 0, for example, we give it code Kasami code 0, C0, where W0 is equal to C0. Neuron 1, we C1 equal to W1 equal to C1, and so on all the way to the last neuron. By doing this and by fixing the weight, so we are not allowing the classification layer now to adjust or learn or to modify these weights, we are applying a constraint on the network and kind of pushing it, encouraging it, forcing it to learn a specific latent representation for each data class. Because in order for the overall, the output, the classification layer, the classification output of the network to be correct as we wish. For example, if we have an input xj that belongs to data class j, we need the final output of the network yj to be maximized, while all other outputs to be minimized, y0, y1, yn minus 1, all other output to be minimized, and only yj to be maximized. That means we need yj equal hj, wj to be maximum, while all otherwise to be minimum. This is perfectly satisfied and achieved if hj is equivalent to is equal to Cj, since Wj is equal to Cj, and if we have Hj as well equal to Cj, then that means Yj will be maximized while all otherwise will be minimized. So by fixing the weights of the classification layer to these orthogonal Kasami codes, we encourage and force the network to output a latent representation for each data class that is equivalent to the Kasami code associated with that specific data, with that data class. And by this way, the overall output of the network, the classification output, is going to be correct, or as correct as as we wish. It will be the correct classification. And this is the basic idea. So we are fixing the weights of the classification layer and allowing the network to learn these codes for each data class. We evaluated this into in four of the popular image data sets, basically MNIST and Fashion MNIST and CFAR10 and Street View House number. And we constructed a small convolutional neural network consisting of 7 convolutional layers. And we trained this network 3 different times, where in each time, in the first time, we attached a conventional classification layer to the network. The second time, we again used a conventional classification network, but preceded by a dropout layer. And finally, with our we trained the network with our orthogonal classification layer, where the weights of the classification layer were fixed to a set of Kasami sequence. And as we can see, the network not only succeeded in achieving this constraint of outputting these specific codes as latent representation for each data class, but it also provided higher classification accuracy compared to the conventional classification layer called plane here, named plane here, and the one with the conventional with dropout as well. And we believe this is mainly because by using the orthogonal classification layer this way, we are forcing the network to learn a specific latent representation for each data class that is equivalent to these orthogonal codes. And since these orthogonal codes are designed to be well separated and very orthogonal to each other, this provides an easier or better separable latent representation domain. And as we can see here in this slide, at the left, this is the visualization using TSNE of the latent representation of the network generated using the conventional classification layer. And to the right, these are the latent representation, visualization of the latent representation using our proposed orthogonal classification layer. To conclude at the end, mainly we are proposing an orthogonal classification layer that can be used as an output layer for the network, and it allows the network to train and provide higher accuracy compared to the conventional classification layer. And more importantly, this orthogonal classification layer allows us to have control over the latent representation generated by the network or learned by the network for each data class, which is a big advantage that we are intending to capitalize on and utilize in future work, because now we have control over the latent representation generated for each data class. So we know what the network is not allowed to output any arbitrary latent representation for each class, but it is constrained to output a specific latent representation for each data class that is known beforehand to us. And this opened the door for many possibilities, such as developing new and alternative loss functions, because now we don't have only the final label available for us in the supervised learning scenario at least, but we have also the latent representation expected for each data class. Also, this can, since the latent representation are representing the feature map or the feature set for each data class, this can provide good way of designing a feature map, feature sets that is more explainable or interpretable or have whatever advantage that we would like that the designer of the network requires. Thanks a lot, and if there's any questions, I would be happy to receive them. Thank you.